Quadratic programming is an optimization technique that minimizes a quadratic function subject to linear equality and inequality constraints. In this video, we extend quadratic programming into mixed-integer quadratic programming. Let's start with a quadratic programming problem. Maximize line x squared plus y squared with x and y being real numbers subject to linear constraints. In this case, x and y are decision variables. We can select any real numbers inside the feasible region. In a moment, we will see what happens as we change one of them to be an integer. Here are three boundary lines corresponding to our inequality constraints. 3x plus 2y equals 18, negative x plus 2y equals 2, and x equals 3. Together with x and y being non-negative, we build the polygon as you can see here. The shaded area is our feasible region. Every point inside satisfies all linear constraints simultaneously. The objective x squared plus y squared produces circles, while line x squared plus y squared produces ellipses that are narrow in the x direction and wide in the y direction. Starting with the ellipse at b equals line, where we are inside the feasible region, we will expand outward to find the farthest point we can reach. At b equals 36, the ellipse is starting to push against the right and upper corners of the feasible region. We can still keep moving. By b equals 81, the ellipse is very close to the boundary. One more push and we will find the optimal solution. The largest ellipse still touching the feasible region is the tangent at the corner x equals 3, y equals 4.5, giving an objective value of 101.25. That's a continuous quadratic programming solution. Instead of continuous x, right now we restrict decision variables x to be 0 or 1. It's a binary integer variable. Y keeps continuous. This is actually a mixed integer quadratic programming because the decision variables include both integer and continuous variables. With x required to be 0 or 1, the feasible region is no longer a polygon. We have two vertical lines, x equals 0 and x equals 1. Every feasible solution must be selected from two vertical lines. Expanding the ellipse outward from the origin, we look for the largest value of b. At b equals 65.25, the ellipse just touches a line of x equals 1. Surprisingly, the optimal mixed integer quadratic programming solution is x equals 0, y equals 9, not as x equals 1 as you might expect from the heavy weight on x. Let's consider a more complicated objective function. What if the objective also includes a cost term, 4 times x times y? The shapes are no longer axis-aligned ellipses. The cost term rotates ellipses as you can see by comparing the two plots side by side. On the left, line x squared plus y squared produces axis-aligned ellipses. On the right, introducing 4xy rotates the ellipses, meaning the optimizer is now reverted for increasing x and y together, not just independently. Here's a new mixed integer quadratic programming with a cost term added to the objective function. The small ellipse at b equals 9 keeps inside the feasible region. At b equals 36, the ellipse is expanding. By b equals 81, the ellipse is very close to touching the line of x equals 1. The cost term is clearly pulling the optimal solution to the right, different from the diagonal objective we discussed before. The largest ellipse touching the feasible side makes contact at x equals 1, y equals 7.5, giving an objective value of 95.25. A small change in the objective function can completely redirect the optimizer. Let's compare the two mixed integer quadratic programming problems side by side. Without the cost term, maximizing 9x squared plus y squared gives the optimal solution x equals 0, y equals 9, as far from the origin as possible. On the right, as we have 4xy in the objective, the optimal solution becomes x equals 1, y equals 7.5. Same feasible set, same constraints, but the cost term completely changes the optimal solution. Thanks for watching this video. Feel free to reach out.